On June 24th, the earthquake map seemed to erupt in three different parts of the world. A magnitude 5.6 earthquake shook Northern California. A devastating pair of magnitude 7.2 and 7.5 earthquakes struck Venezuela only 39 seconds apart. About 25 minutes after the Venezuelan doublet, a magnitude 6.9 earthquake occurred off northeastern Japan. The locations were separated by oceans and continents. The timing made them look connected. For several hours, earthquake alerts, videos, and maps created the impression that the entire planet had entered one violent seismic episode. California, the Caribbean margin, and the Japan Trench appeared together on screens that compressed the world into a single image. Scientists reached a different conclusion. The California, Venezuela, and Japan earthquakes were not one global cascade. They occurred on separate fault systems, within different tectonic settings, and at distances too great for ordinary static stress transfer to connect them. One connection was real. The two Venezuelan earthquakes formed a doublet. The first large rupture altered stress in the same regional fault system, and the second, larger rupture followed before the ground had stopped shaking from the first. That is the title's central reversal. Several significant earthquakes happened within hours, but the map grouped together two very different phenomena: a physically connected local sequence in Venezuela and independent earthquakes occurring elsewhere on an active planet. The original title, Earthquakes All Over the Planet, therefore overstates the evidence. Earthquakes do occur worldwide every day, but three prominent regions shaking close together in time does not show that the whole planet has entered a new seismic state. What is happening right now also needs a date. The cluster occurred on June 24, 2026. It remains important because it offers an unusually clear demonstration of how coincidence, aftershock physics, global monitoring, and social media can combine to create the appearance of a worldwide pattern. The strongest defensible title is Earthquakes Hit Venezuela, California, and Japan within hours, but they weren't connected. That does not make the day ordinary for the people affected. The Venezuelan sequence produced catastrophic destruction and a prolonged humanitarian crisis. Northern California experienced its strongest earthquake in that local area in decades, with injuries, power interruptions, and widespread alerts. The Japanese earthquake delivered strong shaking to northeastern Honshu, though the offshore event did not generate a destructive tsunami. The consequences were different, because earthquake risk is not determined by magnitude alone. Depth matters. Distance from population matters. Building strength matters. Soil, slopes, fault direction, time of day, and secondary hazards matter. A smaller earthquake beneath vulnerable infrastructure can create more disruption than a larger earthquake far offshore. A deep earthquake can be felt across a wide region while producing less intense surface shaking near its epicenter than a shallow event of similar magnitude. The first narrow answer is now clear. The events looked connected because humans saw them together, not because one rupture traveled around the planet and broke the next fault. The larger question is more interesting. How can scientists tell the difference between coincidence and genuine earthquake triggering when seismic waves from a large earthquake really do travel through the entire Earth? For documentaries that follow the physical mechanism instead of the viral pattern, subscribe and stay with us. The answer begins with the exact sequence of events. Northern California moved first. The magnitude 5.6 earthquake occurred near Redwood Valley in Mendocino County, within a broad region shaped by the complicated interaction of the Pacific and North American plates. It was a significant local earthquake, but its rupture was limited compared with the events that followed in Venezuela. Hours later, the first Venezuelan earthquake struck near San Felipe. USGS analysis later classified the magnitude 7.2 event as a foreshock in a double event. 39 seconds later, the magnitude 7.5 main shock ruptured nearby. The two events were separated by only a short distance and involved the same active plate boundary region between the Caribbean and South American plates. Their timing, location, and stress interaction made a physical connection plausible and measurable. Then, roughly 25 minutes after the Venezuelan main shock, the magnitude 6.9 earthquake struck offshore of Kuji in northeastern Japan at a depth of several tens of kilometers. That earthquake occurred in one of the world's most active subduction environments, where the Pacific plate descends beneath northeastern Japan. It did not require Venezuela to make it happen. The Japanese fault system had been accumulating its own tectonic stress over years, decades, and longer. The Venezuelan rupture did send seismic waves through Japan, as every large earthquake sends waves across the globe. But the arrival of waves is not proof that those waves triggered the rupture. Scientists look for timing relative to wave passage, changes in local seismicity, fault readiness, stress amplitude, rupture mechanism, and statistical behavior. They compare the observed sequence with what would be expected from the ordinary background rate. The event times also expose the illusion created by time zones. A quake reported on Wednesday afternoon in California Wednesday evening in Venezuela, and Thursday morning in Japan may look spread across different dates locally, even though the global catalog records them on one UTC timeline. Social platforms then reorder those reports by engagement rather than origin time. A viewer can see Japan first, Venezuela second, and California third even when the faults ruptured in another order. The sequence on the screen is not necessarily the sequence inside the Earth. The burden of proof is physical. A dramatic clock is not enough. That principle turns the frightening world map into 3 local stories, each governed by its own faults and its own accumulated stress. The first reason the events were not one chain is distance. When a fault ruptures, it permanently changes stress. The first reason the events were not one chain is distance. When a fault ruptures, it permanently changes stress, most strongly near the broken section. This static stress transfer can increase or decrease the likelihood of movement on nearby faults, especially where the faults are already close to failure. The effect weakens rapidly with distance. The Venezuelan doublet fits this pattern because the 2 large ruptures occurred close together in space and time. The first earthquake changed the mechanical conditions on neighboring parts of the same regional system. The second rupture followed almost immediately. California and Japan were different. They were thousands of kilometers from Venezuela and from each other. The rocky lithosphere is strong enough to store tectonic stress, but it does not transfer a permanent local stress change efficiently across entire oceans in the way a steel bar might transmit force. Seismic waves do travel those distances. They carry temporary dynamic stress as the ground oscillates. A passing wave can squeeze, stretch, and shear faults far from the source. In some cases, those waves trigger small earthquakes, tremor, fluid movement, volcanic unrest, or fault creep in regions already extremely sensitive. This process is called dynamic triggering. It is real. It is also frequently misunderstood. Dynamic triggering does not mean every earthquake occurring after a distant large event was caused by it. The triggered response often begins during or shortly after the strongest passing waves, and it is commonly expressed as clusters of small earthquakes in volcanic, geothermal, or highly fractured regions. Large, remotely triggered earthquakes are much rarer. Scientists must compare the timing and rate of earthquakes against the normal local background. They examine whether the seismicity increased when the strongest waves arrived, whether the affected faults were oriented favorably, and whether similar changes occur after other distant earthquakes. Without that evidence, coincidence remains the safer interpretation. The June 24th events provide an unusually clean comparison. The Venezuelan main shock followed its foreshock in 39 seconds and within the same fault region. The Japanese earthquake occurred later but on the opposite side of the world, in a subduction zone system with its own long history of large earthquakes. The California event had occurred earlier in a different crustal fault environment. The calendar connected them, but the fault geometry did not. Magnitude also distorted how the day looked because earthquake magnitude is logarithmic. A 1-unit increase represents 10 times greater measured wave amplitude and roughly 32 times more energy release. That means a magnitude 7.5 earthquake does not release only a little more energy than a magnitude 5.6. The difference is enormous. Using the energy relationship, the Venezuelan main shock released hundreds of times more seismic energy than the Northern California earthquake, yet both appeared as bright markers on the same online map, often displayed with symbols whose size differences were visually limited. The map was designed to show location and recency, not to reproduce the physical energy of each event at true scale. A second distortion came from the way global earthquake catalogs work. The USGS National Earthquake Information Center locates about 20,000 earthquakes around the world each year, or roughly 55 per day. Most are too small, too deep, or too remote to become major news. Long-term records suggest that a typical year includes around 15 earthquakes in the magnitude 7 range and about 1 magnitude 8 or larger. Those earthquakes do not arrive according to a schedule. Some years contain more than the average, some contain fewer. Some are widely separated in time, while others cluster by chance on the same day. Randomness does not mean the process has no physical rules. Each earthquake occurs because stress on a fault overcomes friction. Randomness describes our inability to predict the exact moment among many faults that are loading independently. Imagine dozens of clocks whose hands move at different, partly unknown rates. Most will ring far apart. Occasionally, several ring close together without one clock activating the others. That is what a statistical cluster can look like. The public rarely sees the quiet comparison days. If earthquakes occur in remote oceans over several weeks, each may generate a brief alert and then disappear from attention. When California, Japan, and a catastrophic Venezuelan sequence occur within hours, they share one news cycle. The human mind then performs a useful but dangerous operation. It searches for one cause. Pattern recognition helps people survive because connected events often do share a threat. Smoke, heat, and a rising wind can indicate one growing fire. Multiple aftershocks around a main shock belong to one sequence. But the same instinct can join unrelated earthquakes merely because they appear close together in time. This is the difference between a cluster on a screen and a connected geophysical system. A connected system needs a carrier. Near a rupture, that carrier may be permanent stress change. At long distances, it may be the transient passage of seismic waves. Within an aftershock zone, it may be a cascade in which each earthquake adjusts stress on nearby fault patches. For the June 24th global cluster, no evidence showed a carrier linking the California, Venezuela, and Japan ruptures into one sequence. The only clear carrier joined the two Venezuelan events. This distinction also protects against a second false conclusion. The ring of fire did not suddenly switch on. Japan and California are both associated with the broad Pacific tectonic system, but they do not sit on one continuous fault. The Ring of Fire is a descriptive belt containing many subduction zones, transform boundaries, volcanic arcs, and crustal blocks. A rupture in one section does not force every other section to move. The Pacific margin is active because many plates interact around it continuously. That activity is normal on geologic timescales, even when one day makes it look newly synchronized. There are rare cases when a great earthquake does alter seismicity far around the world. The magnitude 8.6 East Indian Ocean earthquake of April 11, 2012 is one of the clearest examples. It was an extraordinary strike-slip earthquake inside an oceanic plate rather than a conventional megathrust event. Its rupture sent exceptionally strong long-period waves around the planet. Researchers later found that the rate of large remote earthquakes increased during the following days compared with the expected background. The results showed that global triggering is physically possible. It did not create a rule that every same-day earthquake cluster is connected. The 2012 case required statistical analysis across the global catalog, wave propagation modeling, and comparison with normal earthquake rates. The strongest evidence was not that another earthquake happened somewhere afterward. It was that the worldwide pattern departed from the background in a way consistent with the dynamic stresses generated by an exceptional source. Even then, the mechanism did not behave like a crack racing through the planet. Seismic waves temporarily disturbed faults already close to failure. The distant earthquake still released stress that had accumulated locally. The passing waves may have advanced the timing, but they did not supply the full energy of the later rupture. This is a crucial point. Earthquake triggering does not transfer the main shock's energy into another fault like electricity through a cable. The triggered fault stores its own energy. The wave acts more like a brief mechanical nudge. For a large earthquake to result, the distant fault must already be near the point where friction can no longer hold it. That makes remote triggering difficult to prove from timing alone. A fault near failure might have ruptured minutes, days, or months later without the passing wave. Scientists must determine whether the event rate changed beyond what chance would produce. That is why scientists distinguish a plausible mechanism from a demonstrated connection. The June 24th cluster did not show the distinctive evidence established for the 2012 Indian Ocean case. The California event happened before the Venezuelan doublet. The Japanese earthquake followed, but one later event is not a statistical population. Its timing did not by itself demonstrate that waves from Venezuela initiated the rupture. The event also occurred in a highly active Japanese seismic zone where earthquakes of comparable size are expected over time. The ordinary local tectonic explanation remained sufficient. A second historical example shows how real connected sequences behave at shorter distances. On July 4, 2019, a magnitude 6.4 earthquake struck near Ridgecrest, California. Roughly 34 hours later, a magnitude 7.1 earthquake ruptured nearby on an intersecting fault system. After the larger event occurred, the first earthquake was reclassified as a foreshock. Before the magnitude 7.1 rupture, scientists could not know with certainty that the magnitude 6.4 would receive that label. Most earthquakes are not followed by a larger one. The classification depends on what happens next. The Ridgecrest events were connected by proximity, overlapping stress changes, aftershock patterns, and mapped fault geometry. They were not connected merely because both occurred in California during the same holiday weekend. The Venezuelan doublet presents an even tighter relationship. 39 seconds is short enough that the first rupture's waves and stress changes were still evolving when the second event began. The pair behaved less like two random global earthquakes and more like a complex rupture sequence divided into two major releases. This local cascade explains why the Venezuelan events belong together, while Japan and California do not. Distance changes the physics. Nearby faults can experience both static and dynamic stress changes. Permanent displacement around the first rupture may bring another fault patch closer to failure, while strong waves simultaneously shake the surrounding region. At teleseismic distance, only the transient wave field remains significant. The permanent stress change from the source becomes negligible compared with local tectonic loading. The wave can still trigger a response, but the standard of evidence becomes higher. Scientists search continuous seismograms for small events appearing during the passage of love waves, Rayleigh waves, or reflected body waves. They examine geothermal fields and volcanic regions where fluids make faults especially sensitive. They may find tremor or clusters of tiny earthquakes. That is different from claiming that one magnitude 7 earthquake forced another magnitude 7 earthquake on another continent. The scale of the news can hide this difference. A major global earthquake generates alerts at observatories everywhere. Seismic waves may circle the Earth more than once and appear on instruments thousands of kilometers from the source. The planet really does ring, but a seismometer recording those waves is not evidence that the local fault beneath the instrument ruptured. In rare cases, automated systems have even mistaken arrivals from distant large earthquakes for local events. Human review and improved algorithms remove those phantom detections. This is another reason raw earthquake maps require interpretation. The map is a measurement system operating in real time. Locations and magnitudes can be revised. Automatic events can be deleted. Foreshocks can become ordinary earthquakes if nothing larger follows, or acquire a new label after a main shock. The story changes as the catalog improves. A viral screenshot freezes the earliest version. Science keeps editing it. The midpoint reframe is therefore not that global triggering never happens. It is that proving global triggering requires more evidence than a dramatic sequence of notifications. The world can experience several important earthquakes within hours without entering one planetary chain. And one exceptional earthquake can sometimes trigger distant activity without making every later earthquake part of its sequence. Both statements are true. The difficulty lies in knowing which one the data supports. What scientists watch after a day like June 24th is not whether another country appears on the map. They watch each sequence locally. In Venezuela, the doublet created an extensive aftershock zone and secondary hazards, including landslides, damaged slopes, and disrupted infrastructure. The first questions concern how the two ruptures divided the fault system, which sections slipped, where stress increased, and how the aftershock rate changes with time. In Northern California, scientists map the local rupture, refine its depth and mechanism, and monitor the aftershocks expected after a magnitude 5.6 event. They compare the sequence with known faults and with earlier earthquakes in Mendocino County. Off northeastern Japan, agencies examine the offshore earthquake's depth, focal mechanism, observed intensity, aftershocks, and tsunami potential. Japan's dense land and seafloor networks can separate local wave arrivals from distant seismic energy with exceptional precision. These investigations can continue in parallel without becoming one investigation. Each sequence has its own clock. Aftershocks normally become less frequent with time, although the decline is uneven. A period of quiet does not prove the sequence is finished, and a temporary burst does not automatically mean a larger earthquake is coming. The labels are statistical. A main shock changes stress nearby, increasing the rate of smaller earthquakes above the background. As the crust adjusts, the rate generally decays. Larger main shocks tend to produce more numerous and longer-lasting aftershock sequences. Scientists can issue probability-based aftershock forecasts. They cannot identify the exact time and magnitude of the next event. This boundary matters after a global cluster because fear encourages prediction. Online posts often connect the latest earthquake to the San Andreas Fault, the Japan Trench, the Caribbean boundary, solar activity, planetary alignment, or a supposed worldwide release cycle. The visual evidence can feel overwhelming as dots cover the map, notifications arrive repeatedly, and videos show several different kinds of damage. Yet the long-term catalog provides the necessary baseline. The National Earthquake Information Center locates around 55 earthquakes every day. Better instruments detect more small events than older networks could, while faster communication sends those detections directly to the public. The planet has always been seismically active. Modern phones make that activity visible minute by minute. This creates an information paradox. The more completely scientists observe normal earthquake behavior, the easier it becomes to mistake visibility for escalation. An older global map might have shown only the largest earthquakes after analysts processed the data. A modern system can display small events automatically, revise them in minutes, and deliver alerts to millions of people before news organizations publish a full explanation. The apparent surge can occur in the screen rather than in the crust. That does not mean the hazard is exaggerated. Earthquakes remain capable of catastrophic consequences where vulnerable buildings, steep slopes, unstable soil, and dense populations intersect with strong shaking. The Venezuelan disaster demonstrates that the same global background can produce a devastating local outcome. The correct response is not to dismiss the dots. It is to read them at the right scale. A red marker in Venezuela describes a rupture and its affected region. A marker in California describes a different fault and a different population. A marker near Japan describes another tectonic environment, while the map places them together for awareness. Causality must be earned separately, and the same principle applies to preparedness. People in California should prepare for California's known earthquake hazard, not because Venezuela shook on the same day. Residents of Japan should follow local earthquake and tsunami guidance, because Japan occupies an active subduction margin, not because a global chain has begun. During strong shaking, official guidance remains simple: drop, cover, and hold on. Stay away from windows and heavy objects, and do not rush outside while debris may be falling. Near a coast, local tsunami instructions depend on the earthquake, location, and official alerts. The June 24 Japan event did not become evidence of a planet-wide tsunami threat. Preparedness is local because the hazard is local. Global monitoring supports that local action. The USGS, Japan Meteorological Agency, regional seismic networks, tsunami centers, and earthquake early warning systems turn the first arriving waves into rapid estimates. Early warning does not predict an earthquake before it begins. It detects a rupture already underway and may provide seconds of notice before stronger shaking reaches locations farther away. The June 24 cluster highlighted 3 different monitoring environments. California's Shake Alert Network sent widespread notifications. Japan's mature seismic and tsunami systems rapidly characterized its offshore event. Venezuela's doublet showed the growing role of regional networks, international data, and phone-based alerts where national warning infrastructure is more limited. The technology made the day feel synchronized because alerts crossed borders instantly. The faults did not communicate at the speed of the internet. That is the final title payoff. The planet did not suddenly enter one coordinated earthquake episode. A locally connected doublet struck Venezuela while independent earthquakes occurred in California and Japan during the same narrow window. The coincidence was unusual enough to capture attention. It was not unusual enough to overturn what scientists know about stress transfer across the Earth. What would change that conclusion? Researchers would need evidence that seismic waves from one event produced a measurable, statistically significant response at the later source. They would examine the arrival time of specific wave phases, local seismicity before and after the passage, fault orientation, stress amplitude, and whether the result exceeded normal fluctuations. This distinction matters beyond one news cycle. Every future cluster will create the same temptation to treat proximity in time as proof of a common cause. The correct first question is not how many places shook, but whether the events share a fault, a stress field, a passing wave response, or a statistically unusual change in seismicity. One earthquake following another is the beginning of a question. It is not the answer. Picture the global seismic network on June 24. In California, nearby instruments record sharp local waves from the Redwood Valley earthquake. Hours later, stations across the world begin drawing the much larger Venezuelan signals. The traces continue moving when the Japanese earthquake adds another set of waves from a different direction. On a screen, the lines overlap. In the crust, the ruptures remain separated by thousands of kilometers and by distinct tectonic histories. Only the 2 Venezuelan events share the close geometry and timing of one sequence. The rest of the planet is doing what it always does. Its plates keep moving. Its faults keep storing stress. And sometimes several independent clocks strike within the same hour.